Okay, guys, final section of this second unit is special functions. Special functions, there's a few that we're going to look at. The first one has a graph here, but all of these special functions can be known as piecewise defined. So piecewise just means the function occurs based on certain domain values. Okay? Now the graph that you have here on the left-hand side of the screen is what's called the greatest integer function. Now you don't use this very often, but this class does mention it. Basically what it is, it's something that shows up in phone bills. Okay, phone bills use this, the mail service uses this, and what it says is that it gives you the greatest integer not greater than that x value. Okay, so what this means is, let's say I asked you what's the greatest integer, or put 6.8 in your greatest integer function. Well, the number you're going to use is an integer, meaning no decimals, no fractions, that is not bigger than 6.8, but it's the biggest one available. So really you have every number below 6.8, but you want the biggest integer, so that has to be 6. It can't be any bigger than 6.8. That's why 7 does not work. Okay? Now for 7.2, you would get 7, because that's the biggest number that's not bigger than 7.2. And then the same thing here in this bottom one, it's 21.995. It's almost 22, but it's not 22 yet. So you'd have to actually take that back down to 21. And that's what this graph shows. Okay, the closed circle that you see right there, that means that it can equal that value, and the open circle means it cannot. So for that particular one, we're looking at 3 all the way up to 4. Well, it can't ever equal 4 because it's got the open circle. So everything in this middle area right here always goes back down to 3. Okay? Now what that shows you is like a phone company. If you spend, let's take this easy. So we've got 3 and 4 again. For a phone call that costs, $3.30, or even better, a phone call that lasts 3 minutes and 30 seconds, they would actually take it back down to 3 minutes. Now, is that reality? Probably not. They would probably go the other way, which you could do. But like a post office, okay, if it weighs, a certain amount between 4 and 5, they're going to have you pay that amount. Okay, once you hit this next step, so if I were to graph this next step, once I hit right in here, it now jumps up to that value. So it stays flat the whole time. That's your greatest integer function. Okay, it's not widely used in commercial life that you may run into, but it has some very important applications. Alright, the next one is what's called the absolute value function. Now, absolute value is the distance from 0. Now, when you graph absolute value, it is a V-shaped function. You can see here on the graph, I've got this V-shaped graph. Okay, it follows this parent function, f of x equals the absolute value of x, and it has this form, f of x equals a times x minus h plus k. Now you saw a little bit of this when we did quadratics. The h and the k were important values. Okay, the h and the k move things horizontally and vertically. And it's the same thing here. Okay, the h moves things left and right, the k moves the graph up and down. And in the form of absolute value, we also have a vertex, and that vertex is found at the point hk. Now the important thing, remember, h is the opposite of what it looks. Okay, so if you had an x plus 2, the h is actually a negative 2 because of the fact that you have to have 2 negatives to make that a positive. So just watch that and be careful. Alright, so here's what we want to do. We want to be able to take an absolute value function, which is something like this, and we want to be able to graph it. Well, if you take this parent function and just look at it in terms of h and k, there is no h, there is no k. So in this case, h equals 0, k equals 0, which means our vertex is the point 0, 0, which is what I've got on the graph right here. Now, when we did linear functions, we talked about slope. And back up in this equation, we've got this a value. Okay, so you see the a right here circled in green. The a value is just like your slope. It's your rise and your run. And right here, the number that's in that case is 1 over 1. So from my graph, here's my vertex. Okay, I'm back on the graph. And my slope is rise over run. It's 1 and 1. 1 and 1, 1 and 1. And you can see that that makes every one of those points. Now because absolute value cannot be negative, I have to do it both directions, which means I go up 1 and left 1, up 1 and left 1. So it creates that V-shaped graph by going in both directions. Alright, so let's use what we just saw and graph a couple of these. So here we go. There's my graph on the far right. So for this first one, f of x equals absolute value of x minus 3. Well, that right there is your h, that right there is your k. So when we talk about our vertex, we have an h and a k. Remember, for the h, we always do the opposite sign, which is 3. The k, there's nothing there, so it's going to be 0. So my graph starts at the point 3, 0. So I've moved my graph right 3. Now what I look at next is my slope. Well, the slope there has a 1 in front. So that means on my graph, I'm going to go from my initial point, my vertex, and I'm going to go up 1 and I'm going to go right 1. I'm going to go up 1 and I'm going to go left 1. Because this is a V shape, I have to go both directions. And then from each resulting point, I can do the same thing, go up 1, right 1, up 1, left 1, and you can see now you've got your V-shaped graph and you're done. Okay, on this second one. Now this one's a little bit trickier because you have these numbers on the inside. There's a couple ways you can go about this, but I want to try and show you guys the easiest way. Okay? Now in this problem, I want to take my a value and I want to pull it out of the function. So I want the 2 to come out in front. Now if I do that, I have to divide everything by 2. So when I take this 2 and pull it out, it leaves me with a 1. And when I take this 2 and pull it out, it also leaves me with a 1. So my new function is 2 times the absolute value of x plus 1. Well, if I think in terms of h and k, so for my vertex, your h would come from here. Remember, we flipped the sign, it's a -1. Your k comes from there. There's nothing there. That's a 0. So my vertex is -0, 1. And then I look to my a. My a is now 2. So I'm going to go from my vertex up 2 and right 1. Up 2 and left 1. Okay? From each resulting point, I can go up 2 and right 1, and then up 2 and left 1, and I'm now creating my V-shaped graph, and that's your absolute value. Okay, so that's one of the ways. Okay, there are other ways you can take and create a table like we've seen before, and you will get that same value. Alright, moving on to C. I want you guys to pause the video, try those ones out. Don't forget, if this is a K, if that's a K, think about what that does. And remember, when you're pulling that 2 out, you've got to divide. So pause the video, give those a try. We'll come back and look at them in just a second. Okay, let's see how you guys did. So for example C, you got a vertex. We want to find the h and the k. The h, there's nothing in there, so that's a 0. The k is a 6. So I've got the vertex of 0, 6. So I go to my graph, 1, 2, 3, 4, 5, 6 up. That puts me right there at the top of my graph. Now obviously you can scale your graphs differently. This is just the way mine ended up. I look at my a value. The a value is 1. That's your slope. So from here I go up 1 and over 1, up 1 and over 1, and you can continue that on as far as you need to. But that gives me my V-shaped graph, and I'm done. Okay, the final one.
Joshua Weber, would you please return to Mrs. Walker's classroom? Joshua Weber, please.
Sorry about that. Final one is probably the most difficult. Okay, so for this one, we factor out this 2. Okay, the same way we did up in example B. So I take a 2 out of there. When I do 2 divided by 2, I'm left with x. When I do 3 divided by 2, that's just 3 halves. And that's okay. You can have a fraction there. Now, we go through, we have our new problem. We look for our vertex. Our vertex is hk. H comes from there, so that's 3 halves. K comes from there, so that's 1. So your vertex is 3 halves, 1. So on your graph, you go starting at 0. You move right 3 halves, which is 1 1/2. You move up 1, There's your vertex. Now your A value is 2. So from that point I go up 2 and I go over 1. Now since you're going over 1 and you start at a half, you have to make sure you're moving over that full 1 half or 1 value. Okay, so there's 2, 1 again, and going back up to my graph, I'm going to move this up a little bit. I can do the same thing. Up 2, right 1 from that point, up 2, left 1 from that point, and now I've got my V-shaped graph again, and there's your absolute value. So that's how absolute value works, and hopefully that makes some sense. Okay, continuing on. Last part of this is these piecewise functions. Okay, so what we've got here is a piecewise function. And basically what these do is they define differently for different domain values. So if you look at this first one, it says that your graph is going to be negative 2x when x is greater than 1. But it's going to be x plus 3 when the graph is less than 1. Now, this might look a little confusing. I want you just to think of graphing these like a normal problem. So if I gave you this problem, negative 2x, and I asked you to graph this, so y equals negative 2x. Use slope-intercept form. So y equals negative 2x plus b, which is 0 in this case. Okay, so think about how that was graphed. Your b value would be 0. Your slope is negative 2, so you go down 2, right 1, down 2, right 1, and you've got potential to do that. You've got this graph right here. Okay, then we look at this second one. If this was y equals x plus 3, so there's your b, there's your slope. So we start up at 3. The slope is 1. So I go up 1, right 1, up 1, right 1. I could go up or down 1, left 1, and I end up with that graph. Now the tricky thing about this is we now have to look at what the domain says. So I'm going to erase this so we can see the domain. Now for this first one, this top one, it says I want that graph only where x is greater than 1. Okay, so only where x is greater than 1. So we look at our red line, we find where x is greater than 1. X is greater than 1 from here, that direction. So my red graph really only exists at those values. So I'm going to erase everything else. Okay, so I erase everything else. Now whether you guys choose to graph this first or afterwards is fine. But that's all I have of my red graph, because that's where my x value is greater than 1. Now for the other one, I've got the x plus 3 where x is less than or equal to 1. Okay, so less than or equal to 1, again, it's right here, but it moves in that direction. So for my blue graph, I've got to get rid of everything right there. Okay, now the equal to is the big part, because what this is showing me is that when I have 1, it's my blue and not my red. So what that does to my red is it actually is going to put an open circle there to show that it's not equal to. And as you move from left to right along your graph, okay, you can see, and I'm going to do this in green, so try and follow along, but as I move from left to right on my graph, I've got parts of my graph all the way through. So the blue goes to right there, and then it jumps down here and continues on with my red, and that red line and that blue line would continue forever in those directions. And so that's a piecewise. We have a specific function we have to graph, and it depends on the domain where we graph it. Okay, so last one for this. Please pause the video, try this one out, and come back in a second and we'll look at what you did.
Amy Walker, you have a telephone call in the office, please. Amy Walker.
Okay, so hopefully you guys are back. So with this one, we've got 2x plus 1, and that exists where x is greater than 0. So for 2x plus 1, that means we have a y-intercept or a b value of 1. Our slope is 2x, so that's up 2 over 1, up 2 over 1. And this exists where x is greater than 0. So think about what that means. The x is my y-axis, so I'm only going into the positive values, which is right there. And since it's not equal to right there, I have to have an open circle. Okay, so I'm actually going to erase that and try and draw it a little bit nicer, but you've got an open circle right there. Now for the second one, it says that you've got 3 where x is less than 0. That's just the equation y equals 3. Well, that is a horizontal line at 3. So here's 3, and the horizontal line moves this direction into the negatives because it says that it's less than 0. And so what I've got up there on the board is your piecewise defined function, and that's your final graph. Now these are a little bit tricky. You really have to understand what they're asking for in those domains. So if you have questions, contact me, let me know, and we can get together and talk about these in the forum. Alright, good luck with your assignment, and I will see you next time.